So we're going to be talking about descriptive statistics and how to summarize things graphically and numerically. So that being the case, let's move on. And if we've got categorical data, what we are going to do is draw bar graphs or pie charts. And categorical data, if you recall, is data that doesn't have units. It's just counting how many items are in each category. You can describe it as the number of items or the percent of items that are in each category. For example, I could make a pie chart of SSU, how many are freshmen, how many are sophomores, how many juniors, how many are seniors, just counting the number of people in each group. That's not what we're going to do today. In fact, some of the whole homework problems are about that, but I think that part is very well covered in chapter 2. What we're going to do today is talk about numerical data, data that has units. And graphs that we make to describe numerical data are histograms that I bet you've seen before, box whisker plots that you've probably not seen before, and stem leaf graphs that you probably haven't seen before. When you're summarizing numerical data, you summarize it by numbers and by graphs. The numbers fall into two categories. You're either interested in where is the center, where is most of the data. There are 3 ways that we measure the center. The most naive way of measuring the center is the data value that occurs most often. For example, I graded an exam, and most people, the value that occurred most often was 85. More people got 85 on their exam than any other value. That's not very reliable, because if I gave the exam again to a different group of people, 87 might have been the mode, or 92 might have been the mode. The mode varies a lot from sample to sample. It's convenient, but it's not reliable. The median, you organize the data values from smallest to largest. Then you pick the one that's in the middle. 50% of the students got less than this grade, 50% got more than this grade. So if I tell you the median is 85, you know that 50% of the students got more than 85 on the exam and 50% got less. It's the middle value. It's more reliable, definitely more reliable than the mode. The problem is you don't know anything about the students that are on the high end. Maybe 5 people got 100, and you'll never know that because all I'm telling you is the median. Maybe 2 or 3 people got a 42 or 43, and you'll never know that because I only gave you the middle value. The mean is the most reliable. It takes into account every single data value. It takes into account the 42, the 43, and the 5 people that got 100, okay? You take all of your data, you add it up, and you divide by, say, 35, if there's 35 students. It's basically the average of all the data. It is the most reliable. It varies the least from sample to sample. It is also the most tedious to calculate it. You will definitely want a handheld calculator, or if there's a lot of data, you will want a piece of software that will do that for you. So we got 3 ways to tell people what's the center of the data. That's not the only thing that's important, though. we want to know, is the data very spread out, or is it pretty tightly clustered around the center? The range helps us to do that. It's the difference between the maximum and the minimum. Very unreliable. Maybe in this class, somebody got a 42, but in the last class, but the next class, maybe the smallest was only 52. It varies a lot. Better than that is something called the interquartile range. We'll have to talk about that in a moment. It measures the difference between the 75th and the 25th percentile. It focuses on the center of the data, but ignores the edges. The most reliable and the hardest to calculate by hand, essentially almost impossible to calculate by hand, is the standard deviation. It takes into account every single data value. So if we're going to talk about the interquartile range, I have to talk to you about a graph called a box whisker plot. It's very, very popular in statistics. What it does is it orders things from smallest to largest, and there's a marker for the minimum and a marker for the maximum. The next thing it does is it moves itself up to the 25th percentile. It finds the number so that 25% are below that number, and 75% are above that number. Then it moves on to finding the median, the one that's in the middle, 50% below, 50% above, and marches on to find the 75th percentile, 75 below, 25 above. Now, if you were doing this by hand, this is what you would do. You would order the data from smallest to largest. You would probably find the middle piece first. Then you'd take that middle piece and cut it in half, and that would be the quartile 1. You'd take the middle piece and cut it in half. The middle of the upper half is quartile 3. Long story short, what's a box whisker plot? It shows you the middle 50% of the data, bounded by these lines on the edge. The 25th percentile, Q1, the 75th percentile, Q3, and in the middle is the median, the 50th percentile. How do you make the box connected to the minimum and the maximum? By a whisker. You start at Q1 and you go out to the minimum, and that's the lower whisker. You start at Q3, you go up to the maximum, and that's the upper whisker. So there you have your box. If you say to yourself, I wonder how wide this box is. How wide the box is Q3 minus Q1. The width of the box is the interquartile range. It's how wide the box is. If the box is narrow, there's not much variability around the median. If the box is wide, there's a lot of variability around the median. The IQR measures the width of the middle part of the data. The IQR doesn't care about all of this stuff. It doesn't care about all of this stuff. It just cares about the middle of the box. Very important when it comes to homework. So here's a picture, 25, 25, 25, 25. So what's happening here is that Q1 and Q3. Chop off the middle 50% of the box. Another picture. I've introduced something new in this picture, the concept of outliers. Sometimes we have data that have extremely small values or extremely large values, but it's not up to us as people who are non-statisticians to say, I think that's really small, or I think that's really large. We have to have a rule for that. Here's the rule. You calculate a fence, an invisible barrier. You take Q1 and you subtract 1.5 times the width of the box, and you come up with a number. That's an imaginary fence. If you're smaller than that imaginary fence, you're an outlier. On the other hand, on the upside, you take Q3 and you add 1.5 times the width of the box, and there's an imaginary upper fence. If you're bigger than that upper fence, you're an outlier. So we've got a rule that says it's not a wishy-washy thing. There are fences. Below this fence, above this fence, you're an outlier. Here it is. What is the IQR? It's the difference between the third and the first quartile. In layman's terms, it's the width of the box. In layman's terms, it measures the spread or the variability of the middle 50% of the data. It totally neglects the outside 50% of the data. It is not sensitive to outliers. It pretends there are no outliers. It doesn't care. Okay, I grabbed this out of a statistics book. Here is the formula for the standard deviation, just so that you'll know what it measures. You will never calculate it by hand. You take every single data value and see how far it is from the sample mean. You square those values so that positive and negative values won't cancel. Everything will be positive. Then you add all that junk up, divide by something like the sample size, and take the square root to get you back to the original units. What's the takeaway from this? The takeaway is the standard deviation looks at every single data value. It does not throw away the outliers. If there's an outlier in there, it will capture it. It'll put it in its formula and make it the standard deviation bigger. Outliers make the standard deviation bigger. It's giving the word, it's saying, there are some things out there that are a lot further away from the mean than you think they are. So skipping ahead to graphs. There are two graphs besides the box whisker plot that are very popular. You might not have heard of this one. This is a stem leaf graph. So I have data that has 2 digits, games, points earned in games during a basketball season. I want to put this into a graph. I could make a box whisker plot out of that. But when I look at a box with a whisker plot, I only see some summary stats, the median, the quartiles, the whiskers. There's a lot of stuff I don't see. If I want to see all of the data values, what I will do is I will capture the tens digit, and those tens digits will be the stem. So there's a stem of a 1, a 2, a 3, a 4, and a 5. So I've ordered my data from smallest to largest. I think the smallest data value was 12 points. What I do is I put the 1 on the stem and the 2 on the leaf. Tens on the stem, units on the leaf. This would be read 20. This would be read 33. This would be read 51. What's good about the stem leaf graph is you can read every data value from the graph. You don't lose any information. What is bad about it is if you have 1,000 units, can you make a stem leaf graph? No, it would go off the paper. It's good for small data sets. It's not practical for large data sets. So here's an alternative. I bet you've seen this before. It's a histogram, daily high temperatures. So what we've done basically is we've made a numerical variable into kind of sort of a categorical variable. We've created some categories, some bins, some classes. We've counted how many days are between 10 and 20, between 20 and 30. And so we've made little categories. And then we've counted how many days in each category. And we've made something that looks like a bar chart, but it's a histogram because this is 10 up to, but not including 20. And then we skipped from 20 up to not including 30 and so forth. So these upper boundaries are in the second bin, not the first. So the difference between a histogram and a bar chart is the bars are all separated, the little discrete bars. A histogram is a nice, smooth graph that doesn't have no gaps. These are regular outliers, 1.5 IQRs from the boundary. Sometimes you have outliers that are really, really, really extreme. They are so extreme that you're going to have a big fat asterisk, not a little dot, but a big fat asterisk to indicate they are extreme. They are 3 IQRs from the boundary values. Outliers do damage to the mean. They increase the mean. Low outliers make the mean smaller. The median doesn't care. The median doesn't care about the outliers. It only looks at the middle 50%. Outliers always increase the standard deviation. The standard deviation says, way up, wait a minute, there's an outlier. That's really far away from the mean. The standard deviation gets bigger. It doesn't affect the IQR. So here's the takeaway. If there are outliers, the mean and median are better than the mean and standard deviation. Okay, last concept. We'll start with the bottom graph. I bet if I said this was symmetrical, you would know what that means. Can anybody remember from maybe art or some other? It's rounded. Rounded is good. If you were to connect the dots here, it would be a rounded graph. And what about the left side and the right side of this rounded graph? Would they be the same or different?
The same.
The same. Okay. In other words, if you were to put, if this was a piece of paper and you put a line down the middle here and you were to fold it, the left-hand side would plop right on top of the right-hand side. The left side looks like the right-hand side. Data sets that are not symmetrical would have a graph possibly looking like this, where if you were to put a line down here right through the mode and fold, would the left side plop on top of the right? No. The right side would have what? More stuff. It would have more bars, so to speak, more bends. We call this skewed, and we call it skewed to the right. The right-hand side has more data. Or we'll call it skewed to the positive side. When it's skewed to the positive side, the median would be somewhere in here. And the mean would be somewhere over here. So the takeaway from this is when it is skewed to the right, the mean is bigger than the median. The mean is influenced by all of these large values. Conversely, if it's lopsided like this, it is skewed, but now your bends are on the left-hand side. This is skewed to the left, and the median would be about here, and the mean would be over here, because the mean is influenced, it's dragged down by all of these small values. So when it is skewed to the left, skewed to the low end, the mean is less than the median. It's really counterintuitive. Sometimes people think that because the peak is on the left, they'll think this is skewed to the left. It's not where the peak is. It's where the majority of the data is. Skewed to the right, majority of the data. Skewed to the left, the majority of the data. Symmetry, no difference. Positive skew, most of the data is over here on the right. Negative skew, most of the data is over here on the left. So you can see skewness on histograms, you can see it on box plots. So if your distribution is skewed, it's going to be a problem. The mean and the standard deviation aren't going to be representative of the data. They're going to be inflated or deflated. So you're going to prefer the median and the IQR when you have skewed distributions. If it's symmetrical, go with the mean and the standard deviation.